The age of hypersonics is here. Spacecraft are no longer the only vehicles that can travel at 5 times the speed of sound or faster. And as these flight regimes become more common, there's a growing need for accurate mass property measurements. If a hypersonic vehicle is even slightly off balance at those speeds, it can catastrophically fail. This project focuses on the need to design and build a spin balance mechanism for measuring the center of gravity of a payload. Hello, I'm Cameron Crowley and I'm the team lead for this project. I'm majoring in aerospace engineering with a minor in materials science and engineering.
Hi, I'm Casey Kozlowski. I am the team procurement lead. I am majoring in electrical and computer engineering with a minor in math.
Hello, I'm Hamad Al-Hinai. I'm majoring in mechanical engineering.
Hi, my name is Nicholas Gello, and I'm majoring in electrical and computer engineering.
Hi, my name is Aaron Folkerts, and I am the sponsor liaison for this team, and I'm a major in aerospace engineering.
My name is Wyatt Prentice. I'm an aerospace engineering major, and I'm minoring in mathematics and mechanical engineering.
In collaboration with our sponsor, Northrop Grumman Space Systems, we laid out functional requirements that the project was to fulfill. We were tasked with designing and building a system that measures the center of gravity of a payload, displays said measurement, and the relative accuracy of the measurement, along with the magnitude and location of a counterbalance mass. This information is then provided to the user through a graphic user interface. The system must also include an emergency off switch, have user calibration capabilities, portability, suitably operate in a lab environment, and have a minimal number of separate parts. 2 additional bonus goals, time permitted, were to return calculations for moment of inertia and product of inertia, though these were not required. We first approached the problem by conducting market research. Currently, available machines that can measure these values cost thousands of dollars per day to rent and maintain. For our sponsors to procure one would require millions of dollars. We did our best to break down their method to both do away with over-engineered solutions and to focus on the first principles that could get us our CG value.
The system requirements we rendered from the functional constraints were focused on a working subscale prototype. The proof of concept that successfully measured CG corrective mass, was able to be calibrated, was portable, and could be upscaled would be the latchkey to this problem.
The team brainstormed 3 designs that took advantage of controllable motion and different measurement techniques to calculate the center of gravity. These point designs were compared in a decision matrix, and eventually the best methodology was chosen due to its manufacturability, algorithm feasibility, and scalability. Our novel design takes advantage of the conservation of angular momentum, a current sensor, and 3 motor encoders to iteratively locate the center of gravity. Like how a figure skater moves their arms to change their moment of inertia, our system of 3 nested shafts does the same thing. Through a multi-step process with live data calculations, the system can find the center of gravity. A turntable shaft is coded to hold a constant angular velocity with the other 2 motors following suit. Telling the 2 other motors to change their speed relative to the turntable motor causes linear plate motion. The plates move along a predetermined path to find the system's center of gravity. As the orthogonal plates move in and out, our data acquisition system measures current versus time. With this graph that we created, we can find the point in time at which the center of gravity of the payload is as close as possible to the axis of rotation. The key is that this point in time is when the current drawn to the turntable motor is minimized. Finally, we can use motor encoder data to find how far each of the plates had displaced at that critical time. And that will tell us where the payload was moved to. And then using simple math, we can calculate where the center of gravity of the entire system lies. Then, using the parallel axis theorem and other algorithms, we can separate out the center of gravity of the payload from the rest of the system.
Several prototypes and design iterations followed. Once presented to and accepted by our sponsor, our team went to work to actualize our design. During the manufacturing process, many system requirements were proactively fulfilled, such as portability. Upon assembly completion, a series of critical tests were used to verify our design requirements. At the system level, we analyzed, tested, inspected, and demonstrated design validity. Safety was upheld with a series of specific acceptance test procedures to minimize risk.
The spin balance successfully verified all system requirements except for the center of gravity calculation. Our payload CG was inaccurate due to the system center of gravity having noticeable error. Using hand calculations, we verified that our payload center of gravity isolation algorithm was correct. Qualitative investigation revealed a rough spot in the thrust bearing. This resulted in an oscillatory friction behavior whenever we assumed a constant kinetic friction. This variation in friction resulted in an inconsistent torque at constant velocities. The outcome was a system center of gravity being far off from the expected center of gravity of the system at 0. Once we fed in the center of gravity of our system, the non-zero center made the payload center of gravity far off from the expected value. These issues with the thrust bearing could be remedied by ensuring kinetic friction is constant under constant velocity. Constant kinetic friction could be achieved with tighter tolerances, higher quality components, and cleaner interfaces.
This project comes with multiple deliverables. What we will be delivering to our sponsor is a working prototype, a final report, technical data package, test data and procedures, a user manual, software, and a document that details upscaling and improvement recommendations.
What we have discovered is that in the end, our novel nested shaft system could work if we could ensure constant kinetic friction. This obstacle is the design point challenge for many industry companies that make spin balance mechanisms. And this is why so much cost is associated with the mitigation of friction, hence building systems such as spherical gas bearings. With further development, the nested shaft assembly could prove to be a more elegant solution for mass properties measurements. An example of these improvements could be a torque sensor on the turntable shaft to measure moment of inertia as well as verify what we're measuring from the motor. Another example would be higher quality materials. A stiffer, higher tolerance assembly made of higher quality steel or magnesium could make a more stable system. And lastly, a big improvement would be a larger testing campaign. With enough time, friction in this thrust bearing could be characterized and then put into our control system to be accounted for. In conclusion, this project has satisfied all functional requirements and 16 out of 17 system level requirements. In conclusion, our team was not only able to design and build a spin balance mechanism, but we were able to test and nearly verify a groundbreaking method for mass properties measurement. Our discoveries in this project have laid the groundwork for further successful developments, and possibly a more elegant solution than current market machines.